the complex number z is equal to x plus I into y, where x and y are the real numbers. Here I stands for square root of minus 1, and f of z or w of z is a complex function equal to u of x comma y plus I into v of x comma y, where u and v are the real functions of the variable x and y. So next one is distance between the 2 points. Let us draw a plane and z0 is the origin and radius is delta. Let me draw a circle with the radius delta. This is delta. Let me choose a point z. Here the distance between these 2 points is definitely less than the radius. So determinant of z minus z0 is less than a delta. So from this we are saying that the distance between the 2 points is denoted by modulus of z minus z0 when into complex plane with the radius delta, the determinant of z minus z0 which is less than delta. This is called the disk, circular disk. And the point z is called the neighborhood of z0, which is near to the point z. Not only this point, we can choose a point from here to here. We can draw a straight line. We can find the distance between the point. Let me call this point as z1. The distance between the point z1 minus z0 definitely less than the radius. And also I can choose a point on the circle. Let me call this point as z3. So the distance between the point z3 minus z0 is equal to delta. If I am choosing a point outside the circle, that means a radius, I can draw a straight line. And let me call this the point as z4. The distance between the point z4 minus z0 is greater than a delta. This is exterior. This is called the exterior. And this is called the interior circle, and this is called the boundary of the circle. And the next one is single valued function. We are saying that a function f of z or it is equivalent to w if we got a unique value. If we got a unique value for w for each value of z. If I am getting a unique value for w for each value of z, then I can say that f of z is a single valued function. And one example we'll consider. Let w is equal to z square. If I substitute z equal to 1, I am getting a value, only one value, unique value, that is w is equal to 1 square is equal to 1. For each value of z, I am getting only one value for w, whereas w is equal to z raised to the power 1 by 2. Suppose z equal to, let z equal to 4, then w is equal to square root of 4 is equal to plus or minus root 2. For each value of z, I am getting more than one value for w. Therefore, this is not a single valued function, but this is a single valued function. This is example for multi-valued function. Next one is, let us see the definition of a limit of the function f of z. A single valued function f of z is said to have a limit L. That means that, let us consider a table of values. The first value is z0. I am getting some solution called f of z0 and z1, and at z1 I am getting a solution f of z1, like this, etc. So a single valued function f of z is said to have a limit L as z approaches to z0 if f of z is defined in a neighborhood z0, and if for every positive number epsilon we can find a positive number delta such that determinant of f of z minus L, which is less than epsilon for all z, given by on the condition 0 less than modulus of z minus z0 less than delta. What does it mean is the difference between the point z and z0 or the point z0 and z1, the distance between the points is less than delta, the condition is hold, and the corresponding solutions f of z0 and f of z1, the distance between f of z0 and f of z1 is less than epsilon. That means that as z0 approaches to z, then the f of z0 approaches the same value and f of z0 is also approaches the same value. If f of z equal to x plus y the whole square divided by x square plus y square, we have to show that the limit does not exist for this function as z approaches to 0. If we are saying that the limit exists for this function f of z as z tends to 0, then for different values or for all the path, the f of z has the same value. So if it is not the same value, then limit does not exist. Let me find a limit for the function f of z as z approaches to 0, and also for all the path y is equal to mx. Set y is equal to mx. So limit x tends to 0, x plus now y is equal to mx raised to the power 2 upon x square plus mx the whole square, which is equal to a limit x tends to 0. We can take x as a common factor and take it outside. Therefore, it is x square 1 plus m the whole square divided by, in the denominator also we can take it x square. The remaining will be 1 plus m square. Cancel the numerator and denominator x square terms. Cancel the x square terms in the numerator and denominator. The remaining is limit x tends to 0, 1 plus m raised to the power 2 upon 1 plus m square. So we are not getting, so f of z does not approaches to the same value for all the path. If I set m equal to 0, I am getting one solution. If I set another value for m, I am getting different solutions for different path. Therefore, limit does not exist for this function as z approaches to 0. The next definition and the next definition is derivative of f of z. A function f of z is said to be differentiable at z equal to z0 if the limit over delta z tends to 0, f of z0 plus delta z minus f of z0 upon delta z exists. The value of the limit is derivative of f of z at z equal to z0. So let us consider one example. Check whether f of z equal to z bar has a derivative. Solution: since or let z equal to x plus iy and delta z equal to delta x plus I into delta y, and z bar is equal to x minus iy. Okay, also f of z equal to z bar equal to x minus iy. By the definition of derivative, we have to find the limit over delta z approaches to 0, f of z0 plus delta z minus f of z0 upon delta z, which is equal to, let me find f of z. Let's call this as f of z. So z plus delta z is equal to f of x plus iy plus delta x plus I into delta y, which is equal to, separate the real and imaginary parts, x plus delta x plus I into y plus delta y equal to x plus delta x minus I into y plus delta y. Substitute the value of f of z plus delta z here and f of z already given, then it is equivalent to. That means the derivative of the function f of z is denoted by f prime of z at the point z naught is f prime of z naught. So limit delta z approaches to 0, x plus delta x minus I into y plus delta y minus of x minus I into y divided by delta z. Delta z is nothing but delta x plus I into delta y. So limit delta z approaches to 0, this plus x, this minus x get cancelled, then minus into minus plus, so this is plus iy, this is minus iy get cancelled, the remaining is delta x and minus I into delta y, and in the denominator we have delta x plus I into delta y. If I set delta y tends to 0, then the remaining part will be tends to 0, the remaining part is delta x divided by delta x. We can cancel each other, it is equal to 1. So if I set first delta x tends to 0, then delta y tends to 0, then what will happen in the derivative of z? Equal to limit delta x tends to 0, then delta y tends to 0. So if I put delta x equal to 0 here, then minus I delta y divided by I into delta y. So this and this get cancelled, is equal to minus 1. The limit values are not unique, therefore the derivative does not exist for this function. If the limit values are same, then we can say that the derivative exists for the function f of z equal to z bar. And next one is a Cauchy-Riemann equation. Next, let us discuss the definition of analytic function. A function f of z is said to be analytic at the point z naught. Z naught, then if it is analytic everywhere or analytic in the neighborhood. The necessary and sufficient condition. The necessary and sufficient condition for, and let me write the points here too. Ux, Ui, Vx, Vy exist. The second point satisfies CR equation, Cauchy-Riemann equation. In short, it is called the CR equation. This is the necessary condition. The sufficient condition is Ux, the partial derivative exists and continuous and also satisfies CR equation. Then it is the function is said to be analytic. Let me check. Let me call one function f of z equal to z bar is analytic or not. So by the previous definition of derivative and one example we have seen, from that we can say that this is not an analytic function everywhere. Why? Because in simply we can say the derivative is not exist for this function. Therefore, the function f of z equal to z bar is not analytic. Or otherwise, I can prove that f of z equal to z bar, it can be written as x minus iy. Now take the real and imaginary part from the given function. The real part is equal to x and the imaginary part v is equal to minus y. Now partially differentiate u with respect to x, u with respect to y. So 1, and we have no y here, therefore when partially differentiate u with respect to y, x is treated as a constant, then the differentiation of the constant is 0. And the partial differentiation of v with respect to x and v with respect to y is respectively, partial differentiation of v with respect to x is 0, since we have no x here, then minus y treated as a constant, then the differentiation of the constant is 0. Then the partial differentiation of v with respect to y is minus 1. So the derivative exists, but let us check whether this satisfies CR equation or not. Ux is not equal to Vy because 1 is not equal to minus 1, but Uy is equal to minus Vx. Though one condition, one equation of CR equation is not satisfied, therefore the given function f of z equal to z bar is not analytic.